Hello everyone, and welcome to Rainmelt University. Today we're going to talk about number systems as they pertain to computers, and we're going to discuss the hows, the whats, and the whys. How they work, what they are, and why we use them. Let's get started. When we talk about decimal number systems, these are something that's familiar to everyone. So when we're talking about decimal number systems, we have digits that range from 0 all the way up to 9. When we talk about a binary number system, we're talking about a much more simplified number system. This only has 2 digits. You have a 0 and you have a 1. These digits are called bits. When we're talking about hexadecimal number systems, we're talking about a number system which has 16 total digits. So let's go ahead and just start with decimal number systems. Decimal number systems are something that we all recognize. We're used to seeing the numbers 0 through 9. If we have to count to a larger number than the 9th digit allows, we add another digit, and that digit represents the next value in a decimal number system. So in other words, it increases our number system by itself. So since we have 10 digits, a decimal number system's second digit represents tens. If we have to add a third digit, then that becomes multiplied by itself again. That means it represents the number 10 times 10, or 10 squared. If we add a fourth digit, it multiplies by itself again, meaning we now have 10 to the third power, 10 cubed, or 1,000 or 1,000. That's how the decimal number system works. Binary operates on a very similar principle, but we have to repeat the addition of new digits a lot more frequently. We only can count up from 0 to 1, so we have to add another digit. That digit now becomes our 2's column rather than a 10's column in decimal. So we now have the number 2. If we have to add another one, that is 2 times 2. So that is our 4's column. If we add our next digit, it becomes our 8's column, and so on and so forth. The reason that computers generally speak in binary is because computers are simple. They really only understand yes-no logic. So when we created this yes-no logic gate, we decided that a 0 was going to represent a negative and a 1 was going to represent a positive. So we only count the binary numbers that are represented by a 1. Any zeros are simply not used. When we're talking about hexadecimal number systems, this same logic applies, but we wanted to find a way of getting 16 digits so we didn't have to add digits as early as the number 10. So with hexadecimal number systems, we decided to start adding letters of the alphabet to represent higher digits than what the decimal number scale allows. Interestingly enough, since there are 16 options, 16 is a number that is represented by the binary number system. All of the values for a hexadecimal digit using 4 binary bits. Funnily enough, 4 bits are referred to as a nibble. 2 nibbles are called a byte, so don't take nibbles of my food, yo. Let's go ahead and flash a number on the screen real quick. Go ahead and pause the video and see if you can translate this number from binary into decimal, and then see if you can translate this number from binary into hexadecimal. I'll wait. You didn't pause, did you? They never pause. All right, let's go ahead and work through it. So this number, or 1101, is representative of 4 binary bits. So if we're converting this into decimal, we know that our final column is representative of the number 2 to the power of 0. We only have 2 options, 0 or 1. So we can't even count up to the number 2. So it has to have a maximum value of 2 to the power of 0, which is 1. This also allows us to have odd numbers, which doesn't really exist when you're doing everything by the power of 2, unless you use something like 2 to the power of 0. So we use our number 1 digit, we move up, but the number 2 digit isn't used, so that's unnecessary. We don't count that 0. Our 4th digit is definitely used, so the number 4 bit is turned on, and our number 8 bit is turned on. This number is basically 8 plus 4 plus 1, which equals 13. If you do this in hexadecimal, it's the same basic idea. You're going to first convert this into decimal, the number 13, and then you're going to look at your 13th hexadecimal bit. Since the number 10 is represented by the letter A, B is 11, C is 12, D is your 13th hexadecimal bit. So this is how you convert from decimal to binary to hexadecimal and back again. It's really easy. Thank you for watching Brainmelt University. This is my first video upload. Please be sure to like, share, or hit the notification bell. Get this message out there to the rest of the people who might be struggling with simple number systems. And I'll see all of you later.